Welcome. So the topic we'll be discussing in this lecture is graphs. So we'll be starting graphs with this lecture. So with what we have discussed in the last lecture, with that we'll be stop discussing about trees. Okay. Now we'll be moving to the next topic, which is graphs, right? So in this lecture, we will discuss the introduction to graphs. Okay. Actually, there are a lot of applications of graphs, not only in computer science. In different fields, graphs are applied, and there are many concepts which are studied through graphs. Even there is a separate course which is called as graph theory. Graph theory. Okay. So, so even computer engineers also used to do that course. Okay. For example, if you take internet can also be represented as a graph. Okay, because every computer or a server, you can call it as a node, and the interconnections you can call as edges. Okay. Or if you take any social media things like Facebook, Twitter, all these things can be treated as graph. Every individual can be treated as a node or a vertex. Okay. And whether there is a relationship or friendship exists between two individual, then we can say there is a edge. Okay. So people study, say for example, if some improvement they are making in Facebook or Twitter or any other social media, how can they make improvement? That will be done only by representing that as a graph, and then only they can study that. Okay. Otherwise there is no way to study. Okay. Right. So the applications of this field is very diverse, and this itself is a subject by itself. This itself is a course by itself. Okay. So we will give a brief. Actually, we'll be discussing graphs for at least another few lectures. Okay. So we will try to understand what are the importance of graphs. So the flow will be something like this. In today's session, I'll be introducing the graph. I'll be little bit telling about the history of the graph. That is graphs. That is when graphs was first used um, for solving some problem. With that, we will start, and then we'll be trying to understand some basic terminology. In today's class, we will understand the basic terminology connected with graphs. Okay. After that, we'll be discussing something called as representation. How will you represent a graph in a computer? See, mathematicians also study the graph, but they study with pen and paper, right? They draw the graph and they understand. But but we are studying these graphs as a part of data structure course. It means we want to implement it through some language, and we want to work on that. Then it should be represent in the computer. Then how are we going to represent that? You cannot draw, and you cannot what you call take a photo and upload it. If you do that, the code cannot understand. So there should be some way of representation. Okay. So what are the various ways of representing the graphs? Okay. Not only in computer science, even mathematicians also, they don't deal with small graphs. Means you can draw and understand, but if the graph is large, it should be represented in some way. So what are the different ways of representation that we'll be discussing? And then we'll be discussing graph traversing technique. Okay. There are two traversing techniques. One is called as depth first search, the other one is called as breadth first search. That two things that we'll be discussing. Then we'll be discussing something called as how to traverse a graph with minimum movements. Okay, graph may have many edges. You want to visit all the edges. I mean, graph may have many vertex. We want to visit all the vertex, but by passing through minimal edge. How can we do that? So there are some set of algorithms. We'll be discussing those things, right? So this will be the flow. So let us start. Okay. So the first recorded evidence of usage of graph in the history, it way back to 1736. There is a person by name Leonhard Euler. Okay, he used graphs to solve a classical problem which is called as Königsberg bridge problem. Okay, so the problem states that there are four isolated land areas, okay, which are isolated by river, right? It is something like an, what you call, island, different island inside the river. Okay, there are four isolated land areas, okay, which are separated by river, and these land areas are labeled as A to D. Okay, land area 1 is A, 2 is B, 3 is C, and 4 is D. Okay. And all these four land areas were interconnected by 7 bridges. Okay, these bridges are named as A to G. So these are small a to small g, whereas these land areas are named as capital A to D. Okay, right? So this is the situation. Okay, I think it's clear. There are four isolated land areas which are separated by rivers, and these land areas were connected by 7 bridges which are labeled as A to G, small a to small g. The land areas are labeled as capital A to capital D. Now the problem is, what is the problem? What is the problem which Euler is trying to solve? The problem states that, is it possible to starting at one land location, start at one land location. Say you are starting at land location A. Okay, starting at one land location, is it possible to walk across all bridges, all the 7 bridges, exactly once and reach the starting land area? That is the question. Okay, the question is, start at any land location. Is it possible to walk across all the bridges exactly once and reach the starting land area? Yes or no? This is the question. Okay. So to solve this, so this is the pictorial representation of the problem. See, these are the land areas. Okay, A is one land area, right? This is we'll call it as one land area. B is another land area. C is another land area. D is another land area. Okay, all these are the bridges. This is bridge 1, this is bridge 2, this is bridge 3, this is bridge 4, this is bridge 5, this is bridge 6, this is bridge 7. These are the 7 bridges. Okay, the question is, you start from any land area, but you should walk through all the bridges and you should reach to the land area where you have started. Is it possible or not? That is the question. Okay, to solve this problem, actually uh, Euler has used graph. So this is the first time ever graphs were used to solve a problem. Okay, so he represented all these land areas as vertex or as nodes. So how many land areas are there? 4. A, B, C, D. So these land areas were represented as vertex. Okay, and the bridges were represented as edges. So if you see, there is a bridge from A to B. Okay, so that is this vertex. Okay, and also, so if there is a bridge from A to B, it means that there is a bridge from B to A also, right? Okay, okay, fine. So sorry, A to B bridge is different and B to A bridge is different. Okay, so so if you take this as A to B bridge, this is B to A. Okay, right, fine, it's not the same bridge. Okay, and there is a bridge from A to C. Okay, this one if you take, and also there is a bridge from C to A. There is a bridge from C to A. Okay, okay, there is a bridge from C to D. Where is D? Yeah, this is D. There is a bridge from C to D. Okay, there is a bridge from C to D. The same can be used for D to C in the reverse direction. Okay, and there is a bridge from A to D. There is a bridge from A to D. Okay, and there is a bridge from B to F. B to F. Where is B? B is here. Okay, there is a bridge from uh, D to, sorry, B to D. B to D, not F. Okay, so this is B and this is D. There is a bridge from B to D. Okay, So he represented this in a graph format. Okay. So finally, the solution what he gave is, this is a solution. Start from land area B, walk across bridge A to island A, take bridge E to area D, take bridge G to C, take bridge D to B, take bridge F to D. He started at B, but he has not ended at D. And all the bridges were not crossed. Only he is passing through A, E, G, B, and F. Only 5 bridges he is passing through. It means this is not a correct solution. Okay. So then why Euler give this solution? So this is wrong actually. So Euler answered this problem in a negative way. That is, he said that there is no solution exist for this problem. Okay. So what he said is, there is no solution exist for this problem. Okay. So but he proved that why there is no solution. Okay, that we will see. So we have discussed there, Euler has represented the land area as vertex and bridges as edges. Okay. So this is the definition given by Euler for the vertex, for the degree of a vertex. This is the definition given by Euler for the degree of a vertex or a node. The degree of a vertex or a node is given as number of edges incident on it. Okay. So degree of a vertex or a node is number of edges incident on it. Let us calculate the degree of all the nodes. So let's take B. How many edges are incidenting? 1, 2, 3. Okay, 3. Take A. How many edges are coming? 1, 2, 3. Take C. How many edges are incident on it? 1, 2, and 3. Okay. Take D. 1, 2, 3. Okay. So the degree of all the vertex were 3. Okay. So what Euler defined in the sense, a walk starting at any vertex, going through each edge exactly once, and terminating at the starting vertex is possible. So this is what we want to do, right? A walk starting at a given vertex, going through each edge exactly once, edge is nothing but bridge, and terminating at the starting vertex, which is the land area, is possible if the degrees of each vertex is even. It is possible only if the degrees of the all the vertex is even. But in our case, the degrees of all the vertex is odd. In our case, the degrees of all the vertex is odd. But actually, the solution will exist if the degrees of all the vertex were even. Okay. So this is what Euler proposed. Okay. So if such a walk exists, okay, that is, if the degrees of all the vertex, each vertex is even, then such a walk will exist. If a walk, if such a walk exists, then that type of walk is called as Eulerian walk. As it is proposed by Euler, it is called as Eulerian walk. Okay. For this problem, for Königsberg bridge problem, there is no Eulerian walk. For Königsberg bridge problem, there is no Eulerian walk. Okay. So this is the first ever in the history graph was used. Okay. Later, many scientists started exploring graphs, and they started using graphs for solving several types of problems. Okay. So there are huge applications for graphs. Analysis of electrical circuits, because if you take electrical circuits, electrical power will be generated at one area and it will be distributed, right? And at every place there will be some power station. Maybe if you take every town, okay, there will be an EB station where the power is stored and then it is distributed. Okay. So to study on that, to study that, okay, I mean where the vertex should be placed, or how the electric power can be transmitted with less number of cables. To study all those things, actually the entire EB plan, it should be placed as a graph. Then only you can study and you can sort out that problem. So that is what analytical of analysis of electric circuits. Or even if you take in your home also there may be many electrical points. Okay, that can also be studied by using graphs. Okay. Finding shortest path. So this is a very important problem which is applicable at several areas, right? Okay, finding the shortest path. So one of the classical problem is traveling salesman problem. The traveling salesman want to visit n number of cities. So which path he should take? What will be the shortest path for visiting all these cities? Planning project, identification of chemical compounds, statistical mechanics, genetics, cybernetics, linguistics, social sciences. So there is no end. The list is very huge. Okay. So so there are a lot of applications for graph and graph theory. Okay. So with this introduction, let us get into the concept. Okay. Fine. So how would we define a graph? A graph G consists of two things, two sets. What are they? Vertex and edge. Okay. A finite non-empty set of vertex, which we call it as V of G, that is vertex of that particular graph. G represents graph. And a non-empty set of edge, which is called as E of G. Again, E represents edge and G represents graph. Okay. So a graph, so G of V comma E represents a graph, where G is the graph and V is the set of vertex and E is the set of edges. Okay, right? So this is how we define a graph. A graph consists of two sets, vertex and edge, and it is represented as G of V comma E. Basically, there are two types of graph. One is called as undirected graph and the other one is called as directed graph. What is an undirected graph? An undirected graph is one where there is no specific arrow is not given. Okay, that means you can travel in both the ways. For example, this is an undirected graph. So if there is a connectivity from C to D, which means that you can go from C to D and also you can go from D to C. So such graphs are called as undirected graph. Okay, whereas in directed graph, arrow will be given. If there is an arrow something like this B to D, an arrow is given, then it means that this edge is used to only to move from B to D. You cannot use this edge to move from D to B. There is no path exist. Okay, so 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 in an undirected graph, if an edge is represented as V0 comma V1, V0 comma V1 is an edge. Okay, actually V0 is a vertex. Actually V0 is a vertex, right? V1 is an V1 is another vertex. Okay, so V0 comma V1 means it represents the edge which connects V0 and V1. Okay, so if there is an edge V0 comma V1 exists, then it is equivalent to V1 comma V0. That means if you can travel from V0 to V1, then you can also travel from V0 to V1 to V0. If you can travel from V0 to V1, then you can also travel from V1 to V0. Okay, such a graph is called as undirected graph. So an undirected graph is one in which the pair of vertices in a edge is unordered. There is no order. Okay, this is unordered. That is, it is same. That is, you can represent as either V0 comma V1 or you can represent as V1 comma V0. Both are same. Both are same, right? But that is not the case in a directed graph. In a directed graph is one in which each edge is a directed pair of vertices. It is an ordered list. Okay. In a directed graph, V0 comma V1 is not equal to V1 comma V0. Okay. If there is a edge from V0 to V1, then it is just an edge from V0 to V1. That doesn't mean that there is an edge from V1 to V0. Are you getting? So directed graphs are represented with this type of edges with an arrow at the end. Okay, the part with the arrow ended is called as head part, and the part that does not have arrow is called as tail part. Okay, so this is or you can call this is source. So the tail part is nothing but source, and the head part is nothing but destination. Tail part is the source, and the head part is the destination. Okay, so in an undirected graph is an ordered list. An undirected graph is an unordered list of vertex. Okay, where a path exists from V0 to V1 means there is a path exists from V1 to V0 also. But a directed graph, you cannot say that way. Okay, in directed graph, there will be an it will be the path will be represented by an arrow. Okay. So here are some example graphs. Say for example, this is a undirected graph because there is no arrow given. Okay, this is undirected graph, right? This is also an undirected graph, but this is also a tree. So recall the definition of a tree. A tree is a graph without cycle. Okay, A tree is the graph without cycle. So any tree is a graph. Okay, so this is also a graph, right? It not necessarily that it should have a cycle. Okay, all trees are graphs. Okay, so here also there is no arrows, so this is also an undirected graph. Whereas this is a directed graph. Here you can see there are arrow. So there is a path exists from 0 to vertex 0 to vertex 1, and there is a path exists from vertex 1 to vertex 0, and there is a path exists from vertex 1 to 2, but there is no path exists from vertex 2 to 1. Okay, so this is an example. So the graph 3 G3, that is an example for a directed graph. This is a directed graph. Okay, whereas uh, these two are undirected graphs. Okay, right. Okay, so now let us see this. uh, so okay, see, if every vertex is connected with every other vertex, in this graph you see every vertex is connected with every other vertex. 0 is connected with 1, connected with 2, connected with 3. 1 is connected with 0, connected with 2, connected with 3. 2 is connected with 0, 1 and 3. 3 is connected with 2, 0, 1 and 3. So if every vertex is directly connected with every other vertex, that is called as a complete graph. Otherwise it is called as an incomplete graph. These are not directly connected. All the edges were connected in some or other way, but they are not directly connected. So this is called as incomplete graph. Okay, right. So so what are the vertex of the graph G1? G1 contains four vertexes. What are they? 0, 1, 2 and 3. So this is the vertex list of the graph G1. Okay, V represents vertex, G represents graph G1. What are the vertex of the graph G2? It contains 7 vertexes, 0, 1, 2, 3, 4, 5, 6. And what are the vertex of graph G3? It contains 3 vertexes, 0, 1 and 2. Okay, right. And what are the edges? What are the edges of the graph G1? The edges of the graph G1 are, there is a 0 to 1, 0 to 2, this is one edge. Okay, 0 to 3, this is another edge. Okay, 1 to 2, 1 to 3 and 2 to 3. Okay, this is a this is an undirected graph. Okay, so if it is 0 to 1, it also means 1 to 0, right? So that is understood. Okay, so but you see the edges, just use count the edges, how many edges are there, so that it is mentioned like this. This is one edge, E1, E2, this is another edge, E3, E4, E5 and E6, totally 6 edges. Okay, and all the 6 edges are specified here, 1, 2, 3, 4, 5, 6. Okay, similarly if you see the edges of the graph G2, 0 to 1, 0 to 2, 1 to 3, 1 to 4, 2 to 5, 2 to 6. Again, how many edges? 1, 2, 3, 4, 5, 6. 6 edges. Okay, so the edges of an undirected graph are represented by using this bracket. Okay, so by using this normal bracket. Okay, right. Whereas the edges of a directed graph are represented using angle bracket. Okay, or represented using angle bracket. Okay, here you see 0 to 1 means, that doesn't mean there is a path from 1 to 0. No, in this case there is a path, because these are what? Undirected graph. And undirected graph, the edges are represented using this type of parentheses. Okay, or brackets. Okay, whereas in a directed graph, the edges are represented using angle bracket. Okay, so here you have a path from 0 to 1, and also you have a path from 1 to 0. So these two things should be separated, because it's a directed graph. And there is a path from 1 to 2. That doesn't mean that there is a path from 2 to 1. No, there is no path from 2 to 1. Okay, so directed graph, the edges are represented using angle bracket. Okay, right, fine. In a complete undirected graph, the number of edges will be n into n minus 1 by 2. Okay, so this is a complete undirected graph, right? So the number of edges should be equal to n into n minus 1 by 2. What is n here? N is the number of vertex. Number of vertex is 4. Okay. So 4 into 3. 4 into 3 by 2. 4 into 3 is 12. 12 by 2 is 6. So the number of edges will be 6. Okay. Using this formula, you can calculate what will be the number of edges in a complete undirected graph. Okay. The number of edges in a complete directed graph, the number of edges in a complete directed graph will be n into n minus 1. Okay. The number of edges in a complete directed graph will be n into n minus 1. Okay. For example, if you want to make this graph complete, then it should have, already it has how many vertex? 7 vertex. So it should be 7 into 6. Okay. So that is, it should have 42 edges. It should have 42 edges to make it a complete directed graph. Complete directed graph means there should be a direct path from every node to every other node. Okay. This is not a directed graph. I mean, this is not a directed graph. Okay, but if you make it as a directed graph, I'm saying, or let us say this is a directed graph. Okay. So if you want to make it as an complete directed graph, okay, if you make it as a complete directed graph, then this will have how many edges? 6 edges. This will have 6 edges. Okay, right? So 6 edges means how? There will be an edge from 1 to, okay, this becomes 4. Okay, and there will be a 0 to 1 is there now. Okay, and 1 to 2 is there. Similarly, there will be edge from 0 to 2. Okay, and there will be edge from 2 to 0. Okay, 6 edges. Now it becomes a complete directed graph. Okay, so 0 to 1, can you reach directly? Yes. 0 to 2, can you reach directly? Yes. 1 to 0, can you reach directly? Yes. 1 to 2, can you reach directly? Yes. 2 to 1, can you reach directly? Yes. 2 to 0, can you reach directly? Yes. Okay, so if you make this graph as a complete directed graph, then it is having how many edges? It is 3 into 2 edges, n into n minus 1, that is 6 edges. Okay, fine. So a complete graph is a graph that has maximum number of edges. Okay, for an undirected graph with n vertices, the maximum number of edges is n into n minus 1 by 2, whatever we have discussed. For a directed graph with n vertices, the maximum edges will be n into n minus 1. Okay, in the previous figure, G1 is a complete graph. Okay, now we'll be discussing what is meant by adjacent vertex and incident. Okay, if v0 comma v1 is an edge in an undirected graph, then v0 and v1 are adjacent. Okay, v0 and v1 represents a edge. So but that edge connects what? That edge connects two vertices. What are they? v0 and v1. Okay, so if there is a edge, in an undirected graph, if it connects two vertices, then we say that each of these vertices are adjacent to each other. That is, v0 is adjacent to v1 and v1 is adjacent to v0. Are you getting? That's it. Okay, and also we say that the edge v0 comma v1 is incident on vertices v0 and v1. Okay, the edge v0 and v1 is incident. It is incident on both v0 and v1. Okay, so it is this edge is incident on v1 v0 and also it is incident on v1. Okay, but in a directed graph, if there is an edge v0 comma v1, okay, then what we say, if it is a directed edge, if it is a directed edge, it's not an undirected edge. If it is a directed edge, if there is a directed edge from v0 to v1, then we say that v0 is adjacent to v1. v0 is adjacent to v1. Okay, because from v0 you can directly reach v1. Okay, but we say that v1 is adjacent from v0. v1 is adjacent from v0. Okay, for v0 v1 is adjacent. Okay, but for v1 v0 is not adjacent. Okay, because you cannot reach from v0 to v1. Okay, v0 is v0 is adjacent to v1 and v1 is adjacent from v0, right? Both are actually same. v0 is adjacent to v1, that's it, but v1 is not adjacent. Okay, So now we say that the edge v0 comma v1 is incident on v0. Okay, the edge v0 comma v1 is incident on v0 and v1. Okay, but incidence is same. It is incident on v1 and also it is incident on v0. Okay, right? Why incident is same? In the sense, you may ask why it is same. For v0, this is an outgoing edge. Okay, or outgoing edge. For v1, this is an incoming edge. Okay, so there is an incidence. Okay, so incident means it can be either an outgoing edge or an incoming edge. Okay, right? But adjacent means there should be a path from this vertex to this vertex. So v0 is adjacent to v1, but v1 is not adjacent to v0. Okay, v1 is adjacent from v0, right? Okay, but incidence is both the way. It is incident because this edge is an outgoing edge for v0 and this is an incoming edge for v1. Okay, fine. Okay, so next we will be discussing about feedback loops and multigraph. Okay, what is a feedback loop? If a node is pointing to itself, if a node is pointing to itself, that is called as a feedback loop. Okay, for example, here 0 is pointing to itself, 1 is pointing to itself, self edge, or it is called as self edge. If there is a self edge for a node, then that is called as feedback loops. Okay, and what is meant by multigraph? Multigraph means if there are multiple edges available between two vertex, then that is called as multigraph. Here you can see there are multiple edges available between. See, this is an undirected graph, right? So if there is an edge from 1 to 3, then also there is edge from 3 to 1. But if you see here, there is a one edge from 1 to 3, and there is another edge in the same way. So this is a multigraph. Similarly, there are three edges between 2 and 3. So these are multigraphs. Okay. Even if you take that Euler's problem, uh, whatever we have discussed here, this is also a multigraph. This is also a multigraph because you see there is a path from A to B. Again, there is another path. Similarly, here also there is a path. So this is also a multigraph, right? So, but in the graphs, whatever we are going to discuss, we will not be discussing about feedback loops and multigraphs. That is, we will not be discussing graphs which contains feedback loops and multigraph. So that we are discussing this. Okay. Feedback loop means self-edged. That is an edge pointing to the same node. And a multigraph means multiple edges existing between a pair of nodes. That is called as multigraph. Okay. So we'll be in the in further in the future things whatever we are discussing, we'll not be discussing any graph with self edge and with multigraph, right? Okay, fine. Next, let us see what is meant by subgraph. Okay, a subgraph of G is a graph G dash. Okay, a graph G dash can be called as a subgraph of G such that V of G dash, that is the vertex of the subgraph G dash, is a subset of V of G. Okay, and E of G dash, that is the edges of the subgraph, is a subset of E of G. That's it. It's very simple, right? The subgraph G of a graph G dash, the subgraph of G is a graph G dash. That is, we call G dash as a subgraph only if V of G dash, that is vertex of G dash, is a subset of the vertex of G, and the edges of G dash is a subset of the edges of G. Okay, right? Fine. So this is how we define subgraph. We are learning certain terminologies. Okay, fine. Then what is a path? What is a path? Say for example, there is a vertex v0. Okay, let us see an undirected graph. There is a vertex v1. Okay, there is a vertex v2. There is a vertex v3. When we say that there is a path exists from v0 to v1, v0 to v3, if there is a path exists from v0 to v1, and there is a path exists from v1 to v2, and there is a path exists from v2 to v3, then we say that there is a path exists from v0 to v3. Okay, so that's what the path says. A path from vertex vp to vq, so you can say this is vp, vertex p, this is vq. Okay, a path from vertex vp to vq in a graph It's a sequence of vertices. It's a sequence of vertices. What are they? VP, VI1, VI2, so on and so forth up to VIN, comma VQ. Okay. So you follow any number of vertex, but ultimately you should be able to reach Vn. If such a path exists, then then we say that there is a path exists. Okay, such that Vp comma Vi1, Vi1 comma Vi2, so on and so forth, Vin comma Vq are edges in an undirected graph. So what does it mean? V0 comma V1 is one edge, V1 comma V2 is another edge, V2 comma V3 is another edge. Okay. So a path exists from Vp to Vq if there is a sequence of vertices like Vp, Vi, dot dot up to Vq. Okay, where Vp, Vi1, Vi1, Vi2, Vi2, Vi3, so on and so forth, Vin, Vq are all edges. Okay, right. The length of a path is the number of edges on it. Then the length of a path is the number of edges on it. So if you take the length of this path, what is the length of this path? The length of this path is nothing but count the number of edges. Number of edges are 1, 2, 3, 3. Okay. So the number of edges are 3. That is the length of this path. Okay. So this is how we calculate the length of a path. Right. So here are some examples of subgraphs. So this is one graph, main graph. All these are subgraph. This is a subgraph of this graph. Okay, because you see this subgraph contains one vertex. That vertex is also available in the complete graph, right? And it does not have any edge. Okay, it may have edge or it may not have edge. If it have an edge, that edge should be available in the main graph. Here it is not having any edge. This is also a subgraph of this graph. It has three vertex 0, 1 and 2. These are available here. It has two edges 0, one edge is, this edge is 0 comma 1, this edge is 0 comma 2. Those two edges are available here also. So this is a subgraph of this graph. This is another subgraph of this graph which includes only this part 1, 2 and 3. Okay, and it includes only these two edges. Okay, so this is also a subgraph, right? This is also a subgraph. It includes all the vertices, but it includes only three edges, this edge, this edge and this edge. Okay, so all these are nothing but this is the graph G1 and all these are the subgraphs of the graph G1. Okay, similarly all these are, so this is a example for subgraph of the undirected graph. This is the example for subgraph of a directed graph. So G3 is a directed graph. Okay, so this is a subgraph. 0 is a subgraph without any edges. 0 to 1 is a subgraph because 0 and 1 is here and there is a path from 0 to 1. There is a directed edge from 0 to 1. That is tail is here, head is here. Here also tail is here, head is here. This is another subgraph. Okay, 0, 1, 2. Path from 0 to 1 and 1 to 2. Here also there is a path from 0 to 1 and 1 to 2. It has just ignored this edge alone. Okay, this is also a subgraph. If you see, all the vertex are there, 0, 1 and 2. All the vertex are there and there is a edge from 0 to 1. Here also we have 0 to 1. There is a this should be 1 to 0. Okay, this is mentioned wrongly. There is a edge from 1 to 0, 0 to 1 and 1 to 0. Okay, and there is no edge here, but still this is a graph. But this is a graph. Okay, this is not, these two are not separate graphs. These are two, they are one graph only. They are not connected. Okay, these are called as unconnected graphs, which we'll be discussing later. Okay, but this is also a subgraph, right, of G3. Okay, right. Then let us discuss what is a simple path. A simple path is a path in which all vertices except possibly the first and the last are distinct. Okay, so a simple path, what does it a simple path in the sense? A simple path is a path in which all vertices should be distinct. Okay, in which all vertices should be distinct except the first and the last. First and the last can be same, but the other vertices too should be distinct. Are you getting? Such a path is called as a simple path. Okay, but remember one thing, even if first and last is also not distinct, then also it is a simple path. Okay, So it is not mandatory that the first and the last should be distinct. It may be distinct or it may not be distinct. Okay, but all the other things should be distinct. Okay, say for example there is a path like this. Say there is a path like this. What you call path is nothing but collection of vertex, right? V0 comma v1 comma v2 comma sorry v2 comma v5, okay, comma v8. This is actually a simple path because all are distinct. There is no repetition. Okay, so this is a simple path. So there is another path v8, v5, v7, v6, again v8. This is also a simple path because only the first and the last vertex are same. Remaining all vertex are unique. Okay. So a simple path means either all vertex should be unique or all vertex except the first and the last should be unique. Okay. So that the definition says that a simple path is a path in which all vertex except possibly the first and the last are not distinct. Possibly means it may be distinct or it may not be distinct. Are you getting? Okay. A cycle is a simple path in which the first and the last vertices are same. Okay. Okay, let us discuss something on a path which is not simple. Say for example there is a path something like this. V0 comma v1 comma v7 comma v6 comma v5 comma v7. This is not a simple path. Why it's not a simple path? Because you see here this vertex and this vertex is same. Okay, what's the definition of the simple path says? Or either all vertex should be distinct or all vertex except the first and the last should be distinct. But here the third vertex and the last vertex are same. So this is not a simple path. Are you getting? Okay. What is a cycle? A cycle is a simple path in which the first and the last vertices are same. Okay. A cycle is a simple path in which the first and the last vertices are same. So cycle is a simple path, but cycles should have the same first and the last vertices. So V0, V1, V2, V3, again V0. This is a cycle because you are going from V0 to V1, then it may be directed or undirected. Okay, again V1 to V2, V2 to V3, V3 to V0. Once again you are going to V0. Okay, so this is a cycle, but a cycle should be a simple path. Okay, that means in between something else should not come, then it will not be a simple path. Okay, for example, again here after v3 if v1 comes, then it is not a simple path. Are you getting? Okay, fine. In an undirected graph G, two vertices v0 and v1 are connected if there is a path in G from v0 to v1. If there is a path, it is not talking about any direct path. Okay, an undirected graph G, and we are talking about undirected graph. An undirected graph G, in an undirected graph G, two vertices, we are only talking about connection of vertices. Okay, in an undirected graph G, two vertices v0 and v1 are connected if there is a path between v0 and v1. Okay, so path can be any way. For example, v0, then it can be v2. Okay, it's undirected. Then it can be v2, then it can be v3, again then it can be v1. So there is a path between v0 and v1, right, via v2 and v3. So that is a, so it means that then v0 and v1 are connected. Okay, in an undirected graph G, two vertices v0 and v1 are connected if there is a path in the graph from v0 to v1. Okay, an undirected graph is connected. When will you call the graph itself as connected? This is the connection of vertices, two vertices. When will you call the graph itself as connected? An undirected graph is connected if for every pair of distinct vertices there is a path from Vi to Vj. Okay, you take a graph and you take any two edge, for all the possible two edges there should be a path available from one edge to another edge. If such a path exists in an undirected graph, then we say that that undirected graph is connected. Okay, right? Okay, for example, these two are connected graph because you take from any two, you take 0 to 1, there is a path, 0 to 2, this is anyway complete graph, so there is no question path exists. But if you take this graph, this is also connected because you take any two nodes, 0 to 4, there is a path 0 1 4, 4 to 2, there is a path 4 1 0 2, 6 to 3, there is a path 6 2 0 1 3. Okay, so you take any two vertex, and if you see a path exists or not, there is a path. So these are called as connected graphs. Okay, but if you see this particular graph, this is not connected. This is not connected because there is no path from this arrow is like this. There is no path from 0 to 2. So this is not a connected graph. Okay, fine, right? Okay, next we'll be discussing something called as connected component. So what is meant by connected component? A connected component of an undirected graph is a maximal connected subgraph. Okay, a connected component of an undirected graph is a maximal connected subgraph. What does mean by maximal connected? Let us see the example. See, this is a see this actually these two things are one graph. Okay, it's not separate graph. This is single graph. This is a single graph. Okay, this is a single graph, right? Okay. Now this is a connected component. What is a connected component? A connected component of an undirected graph is a maximal connected graph. Is a of an undirected graph is a maximal connected subgraph. Okay, right? So a connected component of an undirected graph is a maximal connected subgraph. Okay, see, this is a maximal connected subgraph. Why it is a maximal connected subgraph? In the sense, this part is a maximal connected subgraph, but this is a connected component. Why it is a connected component means if you remove any edge, from this component, actually these two are single one graph. This is one component, this is another component. Okay, if you remove any edge, any one edge from this graph, still this graph is connected. Okay, still this graph is connected, so it is called as connected component. Okay, if you remove this edge, still it is connected. There is a path exists from any of this node to any of the other nodes in this component. Okay, whereas this is a maximal connected subgraph. Why it is a maximal connected subgraph means, now if you remove any edge, this graph will become this component will become disconnected. If I remove this edge, this will become disconnected, or if you remove this, it will become this part will become disconnected. If you remove this 7 will get disconnected. Okay, right? So this entire graph is actually one graph, so you call this is called as G4, and this G4 is not connected. G4 is not connected. Okay, right? So a connected component of an undirected graph is a maximal connected subgraph. Okay, if a particular graph contains a maximal connected subgraph, then that is called as a connected component. Okay, a tree is a graph that is connected and acyclic. What is a tree? A tree is, this is another definition of tree. A tree is a graph that is connected and acyclic. That is, there should be a connection exist between all edges. I mean all vertex. You cannot leave any vertex without an edge. Okay, so a tree is a graph that is connected, and there should not be any cycle. Okay, right. Then see, we discussed what is a connected graph. A connected graph is one in which every edge is directly connected with every other edge in an undirected graph. Okay, in a directed graph is said to be strongly connected. A directed graph is said to be strongly connected if there is a directed path from Vi to Vj and also from Vj to Vi. Okay, a directed graph is said to be strongly connected With respect to undirected graph, we don't use the term strongly connected. We say only connected. It is connected if there is a direct path exists from every node to every other node. Whereas a directed graph is strongly connected if there is a directed path. It's not any via path. It's a directed path from Vi to Vj and Vj to Vi. That is, for every pair of nodes, there should be a directed path in both the direction. Then we say that graph is strongly connected. Okay, right? Okay. Now, what is a strongly connected component? A strongly connected component is a maximal subgraph that is strongly connected. Okay, a strongly connected component is a maximal subgraph that is strongly connected. That is, if you remove one edge also, the tree will become uh, disconnected. Okay, so that is called as strongly connected component. Okay, right? You see here we have discussed connected component. This is with respect to undirected graph. A connected component of an undirected graph is a maximal connected subgraph. Okay, right? See, connected component itself means it is a what do you call? It is not a connected graph. It is already disconnected. Okay, but that disconnected graph has some maximal connected subgraph. I'm getting right. Similarly, here a strongly connected component means again it is disconnected, but and there also it has a maximal subgraph. Okay, so maximal subgraph means where if you remove one edge, it may get disconnected. Okay, fine. So if you see this thing, this is not strongly connected. Why it is not strongly connected? Because what is the definition for strongly connected? A graph is said to be strongly connected if there is a path exists between Vi to Vj and from Vj to Vi for all the vertex. Okay, here you have 0 to 1 and 1 to 0, but you have 1 to 2 only. There is no path from 2 to 1. If you have a path from 2 to 1, and if you have a path from 0 to 2, and if you have a path from 2 to 0, then we say this is a strongly connected graph. Okay, right? But this is a strongly connected component. This is a strongly connected component. Okay, here you see maximal strongly connected subgraph. This is strongly connected because there is a path from 0 to 1. There is a path from 1 to 0. This is also strongly connected, but these two are disconnected. This is one graph only. Okay, right? This is maximally strongly connected subgraph because if you remove one edge, then it is not what you call strongly connected. Then it is not strongly connected. Okay, here it will not get disconnected. It may not be strongly connected. If you remove any one thing, then it is not strongly connected. Okay, fine. Okay, degree. How will we define degree? The degree of a vertex is the number of edges incident on that vertex. Okay, so this is the case for undirected graph. For an undirected graph, the degree of vertex is number of edges that are created from that, or falling, whatever the edges. There is no direction, right? So the number of edges that are incident on that vertex, that is the degree. Okay. For a directed graph, we have two types of degree. One is called as in degree, the other one is called as out degree. Okay, so the number of edges that are uh, the number of incoming edges are called as in degrees for a particular vertex, and the number of outgoing edges are called as out degree. Okay, the number of incoming edges are called as in degree, and the number of outgoing edges are called as out degree. Okay, right? If di is the degree of vertex I in a graph G with n vertices and e edges, okay, right? If di is the degree of vertex I in a graph G with n vertices and e edges, okay, then the number of edges is calculated something like this. E is equal to the number of nodes are n, 0 to n minus 1, okay, di by 2. Okay, that is for all the nodes you count the what you call you calculate the degree. For every node you calculate the degree, okay, and find the sum, and finally divide that by 2. That will give the number of edges. So this is one way to calculate the edge, okay. That is, identify the degree of all the nodes, make a sum of that and divide that by 2. Right. So this is an undirected graph. This you see all these edges have have 3 degrees. This 3 degree, this 3 degree, this is 3, this is 3. Okay. This is also an undirected graph. This node 0 or vertex 0 degree is 2. This vertex degree is 3 because 1, 2 and 3. This vertex degree is also 3, 1, 2 and 3. This vertex degree is only 1, okay, only this one. This vertex degree is 1, this vertex degree is 1, this vertex degree is 1. This is a directed graph. Here if you see, it has 1 in degree is 1, out degree is 1. It has 1 incoming edge and 1 outgoing edge. This also has a in degree 1 and out degree 1. It has 1 incoming edge and 1 outgoing edge. It has in degree node 2 or vertex 2 has in degree 1 and out degree 0. Okay, there is no outgoing edge. Okay, so this is the ADT for graph. So to create a graph, insert a vertex, insert an edge, delete a vertex, delete an edge, check whether the graph is empty or not. Okay, list adjacent, return a list of all vertices that are adjacent to V. Okay, find the vertex that are adjacent to V. Right? Fine, let us stop here. So this is the introduction to graphs. The rest of the thing we will continue in the other classes. Okay, thank you.